In this video, we're going to discuss integration by parts, which is an integration technique that's based on the product rule for differentiation and will allow us to rewrite the integral of some products of functions in terms of other integrals that are more easily computed. To see exactly where the integration by parts formula comes from, we're going to start with the product rule of differentiation. As you hopefully recall, the product rule says that if I differentiate a product of functions, f times g, the resulting derivative is f of x times the derivative of g plus the derivative of f times g. From this equation, we can take an antiderivative of both sides. And on the left side, we'll be taking an antiderivative of a derivative, and therefore we'll obtain the function that we started with. So this anti-differentiating on the left side will just yield f times g. Now, technically, there will be a constant of integration here, but we can just assume that is 0 in this case. We just want an antiderivative, so f times g will work. And on the right side here, we're simply just going to write the indefinite integral of this sum of products. So f times g prime plus f prime g. Now, by using a property of integrals, we can break up the right-hand side of this equation into the sum of two integrals. We can have the integral of f times g prime plus the integral of f prime times g. At this point, we want to rearrange this equation and solve for our first integral here, the integral of f times g prime. And so the integral of f g prime will be f times g minus the integral of f prime times g. With the equation arranged like this, we can see that this integral on the left-hand side, which is the integral of a product of two functions, can be rewritten as the product of the functions f and g minus another integral. And if this second integral on the right-hand side is a simpler function, then we'll be able to evaluate that integral and therefore evaluate the integral on the right side. We can make this equation a little bit simpler by replacing the functions f and g and their derivatives with different variables. So for example, we could let u equal f of x and v equal g of x. And with those substitutions, we can then have du to be f prime of x dx and dv to equal g prime of x dx. Substituting all of these into the equation at the top, we obtain the integral of f times g prime, which is going to be u dv. That will equal f times g, which will be uv, minus the integral of f prime g, or gf prime, if we want to put the derivative at the end, and that would be v du. And so we obtain this formula here, where u and v are differentiable functions, and this is known as the integration by parts formula. This will be the formula that we use. What we will do, the way that we will use it is we will take an integral like the one on the left-hand side of this equation and rewrite it using the functions u and v as the right-hand side of the equation. And in the cases where this formula will be useful, that integral on the right-hand side will be simpler and one that we can evaluate with techniques that we already know. So let's see an example of how the integration by parts formula can be used to evaluate an integral by evaluating the integral of x sine of x. Notice first that this integral is not one that can be done just by using elementary antiderivatives, as we don't know a function whose derivative is x times sine of x. Also notice that substitution is not going to be useful here because regardless of what you let your u value equal, the value of du is not going to be present in this integrand, and you're going to have another factor, another function in terms of x that we can't substitute. And so none of the previous techniques we've seen for integration are going to apply to this particular integral. However, if we use integration by parts, what we need to do is break up the entire integral to be u times dv. And there's always a couple of different ways we can do this. And so let's start by trying to let maybe u be just x and dv being everything else, which in this case would be sine x dx. And we can list these functions down here. U is going to be x, dv is going to be sine x dx. And once we have determined u and dv, the rest of our values in the formula are given to us. Du is going to be the derivative of u, which in this case is just dx, the derivative of x. And v is going to be the antiderivative of sine x, which will be negative cosine x. And so here we want to make sure we anti-differentiate sine to get cosine, since the sine is the derivative of the function v. Now, by using our integration by parts formula, we're able to rewrite our integral, x sine of x, by writing u times v, so x times negative cosine x, minus the integral of v du, which would be negative cosine x dx. And now notice by kind of cleaning this up a little bit, we're going to get negative x cosine x by putting the negative out front. This will become a positive integral of cosine x because we can, again, factor that negative out of the integral, and it combines with the subtraction in front to become an addition. And now we have an integral on the right-hand side, which is much simpler than the original and one that we can evaluate because we do know an antiderivative of cosine. And so we have negative x cosine x. The antiderivative of cosine x is sine x. And of course, since we've just done an indefinite integral, we need to add our arbitrary constant plus c. And so our original integral of x sine x dx is going to be evaluated to give us negative x cosine x plus sine x plus our arbitrary constant c. One thing to observe about this particular example, and really about any integration by parts examples, choosing the value of u at the very beginning determined everything else. Once we decided that x was going to be the part of the integrand equal to u, dv was determined. It was the rest of the integral, sine x dx. And once we had u, we automatically had du, which was its derivative. And once we had dv, we automatically had v, its antiderivative. Once we had all of those values, we substituted it into our formula, and we just evaluated our indefinite integral, in this case of cosine x. This whole process revolved around the fact that we ended up with a simpler function inside the integral on the right-hand side, in this case cosine x being simpler than x sine of x, so that we actually were able to evaluate that integral. It's very possible that depending on our choice of u and v, or u and dv rather, that we end up with a more complicated integral, and that often means that our choice for u and dv was incorrect. So in order to see what happens if we would choose inappropriate values for u and dv, let's consider the same example that we just evaluated correctly. Here we're going to choose u to be sine of x. Recall in the correct version, we allowed u to equal x. And so this is going to be an incorrect choice for u. Once we pick u, everything else is determined for us. dv has to be everything else in the integrand, which would in this case be x dx. Du would be the derivative of sine x, which will be cosine of x dx. And V will be the antiderivative or an antiderivative of x, so x squared over 2. Once we have all of these values, we can use our integration by parts formula. So this will be u times v, which is sine x times x squared over 2, minus the integral of v du, which is x squared over 2 times the cosine of x dx. And what we observe right away is that this integral here is actually more complicated than the one we had in the that we started with. The sine of x and cosine of x parts are pretty similar, but we went from x, a polynomial of x, to a polynomial of x squared over 2. So this polynomial part of our integrand is actually getting more complicated. And so there's certainly no way of knowing what the antiderivative of x squared over 2 cosine x is without doing something else, which is unlike the first approach for this example, where we ended up with the integral of cosine, and that is one that is easily solved using elementary antiderivatives. And so the goal here for any kind of integration by parts problem is that the integral that we come up with on the right-hand side should be either less complicated or, at the very least, not more complicated than our original integral. If we end up getting something like in this example where the right-hand side integral is more complicated than the original, then that means either that we chose the wrong value for u and dv in the original integral, or perhaps we made a mistake, or perhaps integration by parts will not be useful for that particular integral.